You know, I've been asked this question more times than I can count. At dinner parties, after lectures, in elevators, people want to know, can physics really explain where the universe came from? Can equations and experiments tell us why there's something rather than nothing? And here's the thing, it's not just casual curiosity. This question sits at the intersection of our deepest scientific understanding and our most profound philosophical and spiritual beliefs. It's a question that, it gets to the very heart of what it means to be human, right? Now, look, I'm a physicist. I spend my days thinking about strings and brains and the curvature of space-time. But this particular question, the origin of everything, well, this is where physics meets philosophy, where quantum mechanics shakes hands with theology, and where the most rigorous mathematics we have brushes up against the ultimate mystery. So let me be clear about something right off the bat. I'm not here to tell you what to believe about God. That's not what physics does. What I want to show you is something I think far more interesting. I want to show you what modern physics actually tells us about how the universe could have come into being and why that story is so astonishing that it might just change how you think about existence itself. Here's what's truly remarkable. For most of human history, the question of cosmic origins was the exclusive domain of religion and philosophy. You had creation myths, you had theological arguments, you had centuries of debate about first causes and prime movers. And physics? Well, physics was about apples falling and planets orbiting and steam engines. It had nothing to say about the ultimate beginning. But something extraordinary has happened over the past century. Physics has crashed the party, and what it's bringing to the table is not speculation, not wishful thinking, but actual mathematical frameworks, experimental observations, and testable predictions about how a universe, our universe, could emerge from what we might call nothing. Now, I know what you're thinking. Brian, come on. Something from nothing? That violates everything I learned in school. You can't get something from nothing. And you're right to be skeptical. That's the proper scientific attitude. But here's where it gets interesting. When physicists use the word nothing, we're not necessarily talking about what philosophers or theologians mean by nothing. And that distinction, that's where the real fireworks happen. Let me give you a sense of what we're going to explore together. We're going to start with what seems like a simple observation, the fact that the universe exists, and we're going to follow that thread through some of the most beautiful and bizarre ideas in modern physics. We'll encounter quantum mechanics, where particles pop in and out of existence like cosmic fireflies. We'll dive into general relativity, where gravity isn't a force but a curvature in the fabric of space-time itself. We'll explore cosmological models that suggest the universe could be self-creating, requiring no external trigger, no first mover, no divine intervention. And we'll see how all of this connects to one of the most profound questions you can ask. Why is there something rather than nothing? But before we get to the cutting edge, we need to understand how we got here. Because the story of modern cosmology, the story of how physics learned to talk about the beginning, is itself a remarkable tale of human ingenuity and courage. Let's go back about a century. In the 1920s, something astonishing happened. Astronomers using increasingly powerful telescopes began to notice something strange about distant galaxies. They were all moving away from us. Not just drifting, but speeding away, and the farther away they were, the faster they were receding. Now, this was bizarre. If you're standing in a room and you notice that everyone is moving away from you, you might think, okay, I'm at the center. But here's the remarkable thing, and this is absolutely crucial to understand. Every observer in the universe sees the exact same thing. Doesn't matter where you are, doesn't matter which galaxy you're in, you look around and everything else is moving away from you. How do you make sense of that? Well, The only way this works is if space itself is expanding. Not objects moving through space, but space itself getting bigger, stretching like the surface of a balloon being inflated. And if space is expanding now, then if you run the clock backward, everything was closer together in the past. Run it far enough back, and you arrive at something truly remarkable. A moment when all of space, all of matter, all of energy was compressed into an unimaginably small, unimaginably dense state. This is what we call the Big Bang. And let me pause here because the name is actually kind of misleading. When most people hear Big Bang, they imagine some kind of explosion in space, like a bomb going off. But that's not right. The Big Bang wasn't an explosion in space, it was an explosion of space. Space itself came into being in that moment, or at least the space we inhabit. There was no where for it to happen, and there was no before in any conventional sense. Now, you might be thinking, okay, but what caused the Big Bang? And that's a great question. It's the question, but before we can even begin to address it, we need to understand something fundamental about what physics can and cannot do. Physics is extraordinarily good at describing how things evolve, how systems change from one state to another. Give me a set of initial conditions, tell me the positions and velocities of all the particles in a system, and I can use the laws of physics to predict what happens next. That's what we do. But asking what happened before the Big Bang, well, that's like asking what's north of the North Pole. The question itself might not make sense. And here's where things get really interesting. Because modern physics, particularly quantum mechanics and general relativity, has given us ways to think about the origin of the universe that sidestep this problem entirely. They suggest that the universe might not need a cause in the traditional sense. And to understand why, we need to dive into the wonderfully weird world of quantum mechanics. You know, quantum mechanics is now about 100 years old, and I've been studying it for decades, but I still find it astonishing. At the quantum level, the realm of atoms and subatomic particles, the rules that govern our everyday world simply don't apply. And one of the most bizarre features of quantum mechanics is this. Particles can appear out of nothing. Now, let me be careful about what I mean by that. In quantum field theory, which is the framework that merges quantum mechanics with special relativity, empty space isn't really empty. It's seething with activity. The vacuum, as we call it, is filled with quantum fields, and these fields are constantly fluctuating. Energy borrowed from these fluctuations can manifest as pairs of particles, a particle and its antimatter partner that pop into existence, exist for a fleeting moment, and then annihilate back into the vacuum. These are called virtual particles, and they're not just theoretical curiosities. They have real, measurable effects. They affect the behavior of electrons in atoms. They contribute to the vacuum energy of space. They're as real as the keys in your pocket, even though they exist for just a tiny fraction of a second. Now here's the remarkable thing. The Heisenberg uncertainty principle, one of the foundational principles of quantum mechanics, tells us that there's a fundamental limit to how precisely we can know certain pairs of properties. You can't know both the exact position and exact momentum of a particle. And crucially, you can't know both the exact energy of a system and the exact time at which that energy exists. This means that for very short periods of time, quantum systems can borrow energy from the vacuum. The shorter the time, the more energy can be borrowed. And as long as everything gets paid back quickly enough, no laws are violated. So here's the audacious idea that some physicists have proposed. What if the entire universe is the ultimate quantum fluctuation? What if, instead of virtual particles popping in and out of existence, an entire universe popped into existence? Now, I know how crazy this sounds. You're probably thinking, wait a minute, Brian, the universe is huge, it has an enormous amount of energy. How could all that energy be borrowed from the quantum vacuum? And that's a brilliant objection. This is exactly where it gets beautiful. Here's the key insight, and it comes from general relativity. Gravity is weird. In fact, gravity is unique among all the forces in nature because gravitational energy is negative. Think about it this way. If you want to pull two objects apart that are gravitationally attracted to each other, say a rock and the earth, you have to add energy to the system. That means the bound state, where they're together, has less energy than the separated state. Gravitational energy is like a debt, not an asset. Now, here's where it gets wild. If you calculate the total energy of the universe, all the positive energy from matter, from radiation, from the kinetic energy of galaxies moving apart, and you add to that the negative gravitational energy from all the matter, attracting all the other matter, what do you get? Remarkably, the total comes out to be very close to zero, maybe exactly zero. This means the universe as a whole might cost nothing energetically. It's the ultimate free lunch. Let me give you an analogy. Imagine you're deeply in debt. You owe $1 million, but you also have $1 million in assets. Your net worth, zero. You started from zero, and even though you have all this activity, all this money changing hands, your total hasn't changed. The universe might be like that. Positive energy from stuff, negative energy from gravity, and the sum total is zilch. So now we can ask a different kind of question. Instead of asking, what caused the Big Bang, we can ask, given the laws of quantum mechanics and general relativity, what prevents a universe from spontaneously appearing as a quantum fluctuation if the total energy of that universe is zero? And the answer, according to some of the most brilliant physicists working today, is nothing prevents it. In fact, these laws might make it inevitable. Now, I want to be very careful here. I'm not saying that physicists have proven that the universe created itself from nothing. What I'm saying is that we have mathematical frameworks, rigorous, self-consistent theories that describe how this could happen without violating any known laws of physics. These aren't just wild speculations. They're serious scientific proposals that make predictions we can potentially test. One of the most famous of these ideas is called the Hartle-Hawking no-boundary proposal. It was developed by James Hartle and the late Stephen Hawking back in the early 1980s, and it's one of the most elegant ideas in all of physics. Here's the core insight. What if the universe doesn't have a beginning in time? What if time itself emerged along with space? Now this sounds paradoxical. How can something not have a beginning? Well, think about the surface of the Earth. If you start at the equator and head south, you eventually reach the South Pole. But what's south of the South Pole? The question doesn't make sense. There is no farther south. The South Pole is a perfectly well-defined place, but it's a boundary beyond which the concept of south loses meaning. Hartle and Hawking suggested that the Big Bang might be similar. It's not a moment in time preceded by other moments. It's the boundary of time itself. There is no before the Big Bang. In the same way, there's no south of the South Pole. To make this work mathematically, Hartle and Hawking used a brilliant trick. They took Einstein's equations of general relativity and applied them not to ordinary time, but to what's called imaginary time, a mathematical concept where the time coordinate involves the square root of -1. In this imaginary time formulation, the universe doesn't have a singular beginning point. Instead, it's smooth and well-defined everywhere, like the surface of a sphere. When you transform back to real time, what you get is a universe that emerges from a quantum state, expands, and evolves according to the laws of physics. No moment of creation, no need for an external cause. The universe just is. I realize this is a lot to absorb. We're talking about imaginary time and quantum fluctuations and negative gravitational energy. But here's what I want you to take away from this first part of our journey. Modern physics has tools that can address the question of cosmic origins in ways that would have been unimaginable a century ago. We're not just speculating. We have mathematical theories grounded in our best understanding of quantum mechanics and gravity that describe how universes can come into being. Now, does this mean God doesn't exist? No, of course not. Physics can't prove or disprove the existence of God. That's not what science does. But what physics can do is show that you don't need to invoke God to explain the origin of the universe. The laws of nature might be sufficient. Whether those laws themselves require an explanation, whether they point to something deeper, well, that's a different question, and one we'll explore. But before we move on, I want to introduce you to one more idea, because it's going to be crucial for everything that follows. It's the idea of quantum cosmology, the application of quantum mechanics to the universe as a whole. And this is where things get really wild. You see, in ordinary quantum mechanics, we describe the state of a system using something called a wave function. The wave function contains all the information about the system, and it evolves according to an equation, the Schrödinger equation, that tells you how the probabilities of different outcomes change over time. Now, in the 1960s, some physicists asked a bold question: what if we write down a wave function for the entire universe, not just for particles or atoms or even galaxies, but for all of space-time itself? This is an audacious idea. It means treating the universe itself as a quantum object, subject to the same probabilistic rules that govern electrons and photons. And when you do this, when you actually write down the equations and solve them, you find something remarkable. You find that the universe can be in a superposition of different states, just like Schrödinger's famous cat can be both alive and dead, until you look. The universe can, in a sense, be in a state where it both exists and doesn't exist until some kind of observation or measurement collapses the wave function into a definite outcome. Now, I know what you're thinking. Who or what does the observing? Who collapses the wave function of the universe? And that's a profound question, one that gets at the heart of the interpretation of quantum mechanics. Some physicists argue that the wave function of the universe never collapses, that all possible histories coexist in some vast branching multiverse. Others suggest that the wave function collapses spontaneously, or that it's the act of conscious observation that does it. We don't know the answer. But what's clear is that quantum cosmology forces us to confront deep questions about the nature of reality, observation, and existence itself. Here's an analogy that might help. Imagine you're trying to understand a movie. You can describe individual frames. You can talk about how characters move from scene to scene. You can analyze the plot. But to really understand the movie, you need to think about it as a whole, the complete narrative arc, the thematic structure, the beginning and end. Quantum cosmology is like that. Instead of just describing how the universe evolves moment by moment, it tries to describe the entire history of the universe as a single, unified quantum state. And here's where the Hartle-Hawking proposal comes back in. One way to calculate the wave function of the universe is to sum over all possible histories, all possible space-time geometries that have no boundary in the past. You're essentially asking, what are all the ways the universe could have been, given that it doesn't have a beginning in the conventional sense? And when you do this calculation, you get a specific wave function that describes the most probable state of the universe. Remarkably, this wave function predicts a universe that looks a lot like ours, one that starts small and smooth, undergoes a period of rapid inflation, and then expands and cools to form the galaxies and stars we see today. Now, I need to emphasize something here. The Hartle-Hawking proposal is not the final word. It's one idea among several competing proposals in quantum cosmology. Some physicists favor a different approach called the tunneling wave function, where the universe tunnels through a quantum barrier from a state of zero size to a finite size. Others explore ideas involving string theory or loop quantum gravity. The field is very much alive, very much in flux. But what all these approaches have in common is this: they take seriously the idea that the universe can be described using the tools of quantum mechanics and general relativity, and that these tools might be sufficient to explain cosmic origins without invoking anything beyond the laws of physics. So where does this leave us? Well, let me tell you what it doesn't leave us with. It doesn't leave us with proof that the universe created itself from nothing. It doesn't leave us with a complete, tested, final theory of quantum gravity. And it certainly doesn't leave us with a definitive answer to whether God exists. What it does leave us with is something profound and humbling: the recognition that the laws of nature are far stranger, far more subtle, and far more powerful than we ever imagined. When I think about the quantum vacuum seething with virtual particles, I'm astonished. When I think about space-time itself as a dynamical entity that can flex and curve and even come into being, I'm humbled. When I think about the possibility that the universe's total energy is zero, that existence itself is a kind of cosmic accounting trick, I feel a sense of wonder that no amount of scientific training can diminish. But here's the thing. The question we started with, can physics explain the origin of the universe without God? That question rests on some assumptions that we need to examine more carefully. What do we mean by explain? What do we mean by without God? And most importantly, what do we mean by nothing? You see, when physicists talk about a quantum vacuum, we're talking about a state with very specific properties. It has quantum fields, it obeys the laws of quantum mechanics, it has energy fluctuations. Is that really nothing? Or is it just a very subtle, very strange kind of something? And if it is something, then where did it come from? Where did the laws of quantum mechanics come from? Where did space-time itself come from? These are not idle questions. They're questions that philosophers and theologians have been asking for centuries, and they're questions that some physicists, myself included, find ourselves grappling with more and more as our understanding deepens. Because here's what I've come to appreciate. The more we learn about the universe, the more we realize how much we don't know. Every answer opens up new questions. Every mystery we solve reveals deeper mysteries. Let me give you a concrete example. We know that the universe has certain properties: the strength of gravity, the mass of the electron, the speed of light that seem remarkably fine-tuned for the existence of complex structures like galaxies, stars, and ultimately life. Change any of these values by even a small amount, and you get a universe where stars can't form, where atoms don't exist, where life as we know it is impossible. Now, why should the universe have these particular values? One answer is pure chance. We got lucky. Another answer is that there's an infinite multiverse, and we live in one of the universes where the parameters happen to be right for life. A third answer is that some deeper principle, some yet-to-be-discovered law, determines these values necessarily. And a fourth answer, of course, is that they were chosen by a conscious designer for the purpose of creating life. Physics can explore the first three possibilities. We can develop theories that predict multiverse scenarios. We can search for deeper principles that constrain the constants of nature. But the fourth possibility, designed by a conscious agent that's beyond the scope of physics as currently practiced, not because it's wrong, but because it's not a question physics knows how to address with experiments and observations. And this brings us to a crucial point. When we ask, can physics explain the origin of the universe without God, we're really asking two different questions. One is a technical question about whether the laws of physics as we understand them are sufficient to account for cosmic origins. And the answer, I think, is fascinating. Maybe yes. The framework exists. The mathematics works. We have models that are self-consistent and that don't require any external input. But there's a deeper question lurking underneath. Where do the laws of physics themselves come from? Why do we have quantum mechanics and not some other set of rules? Why is there something rather than nothing, not just in terms of matter and energy, but in terms of laws, principles, mathematical structures? And this question, this deeper why, that's not a question physics answers. It might not even be a question physics can answer. You know, Richard Feynman, one of the greatest physicists of the 20th century, once said, "Physics is like sex. Sure, it may give some practical results, but that's not why we do it." What he meant was that the real joy of physics is not in the applications or even in the answers. It's in the questions themselves. It's in the process of pushing the boundaries of human understanding, of confronting mystery with mathematics, of seeing patterns where others see chaos. And the origin of the universe? This is the ultimate question. It's the place where physics meets philosophy, where science meets spirituality, where our most sophisticated mathematical tools brush against the ineffable. And what I find so beautiful about this moment in history is that for the first time ever, we have real, substantive things to say about it. Not final answers, but real progress. Let me paint a picture for you of where we are. Imagine humanity's understanding of cosmic origins as a vast, dark room. For most of our history, we've been stumbling around in that darkness, lighting occasional matches, creation myths, philosophical arguments, theological doctrines that give us fleeting glimpses of our surroundings. But in the past century, we found the light switch, and what we're seeing is astonishing. We're seeing that the universe has a history that we can trace back billions of years. We're seeing that the laws governing this history are mathematical and precise. We're seeing that these laws might be sufficient to explain how the universe came into being without invoking anything supernatural. And we're seeing that the deeper we look, the stranger and more wonderful it all becomes. But here's what's crucial. Turning on the light doesn't mean we understand everything we see. In fact, it reveals just how much more there is to understand. The room is bigger than we thought. There are doors we didn't know existed. And beyond those doors, more questions, more mysteries, more astonishing possibilities. So when I'm asked, can physics explain the origin of the universe without God? My answer is this. Physics can show that the origin of the universe doesn't require supernatural intervention in any obvious way. The laws of nature, as we understand them, seem capable of bringing about a universe without external input. But those laws themselves, their existence, their particular form, their capacity to give rise to a universe like ours, that's a deeper question. And whether you call the answer to that deeper question God or the mathematical structure of reality or something else entirely, well, that depends on your philosophical and spiritual commitments, not on what physics can tell you. What I can tell you is this. We're living in an extraordinary time. For the first time in human history, we have serious scientific theories about how the universe began. We have equations that describe the first fraction of a second after the Big Bang. We have frameworks for thinking about what before the Big Bang might even mean. And we have observational tests, measurements of the cosmic microwave background, observations of distant supernovae, studies of gravitational waves that are beginning to constrain and test these ideas. And here's the truly exciting part. We're nowhere near done. The field of quantum cosmology is still young. Our theories of quantum gravity are incomplete. We're still learning how to make sense of the quantum nature of space-time. Every year brings new insights, new observations, new theoretical developments. The story of cosmic origins is still being written, and the most astonishing chapters might still lie ahead. I want to close this first part with a thought. You know, there's a tendency to see science and religion as competitors, as two different teams fighting for the same territory. And certainly, there are areas where specific scientific claims conflict with specific religious doctrines. But at the deepest level, I think this framing misses something important. Science and religion are asking different kinds of questions. Science asks how things work. What are the laws? What are the mechanisms? How can we predict what will happen next? Religion asks why things are. What is the purpose? What is the meaning? How should we live? These questions touch, they overlap, they inform each other, but they're not identical. When physics proposes that the universe could emerge from a quantum fluctuation without external cause, it's answering a how question. It's saying, here's a mechanism that doesn't violate any known laws, but it doesn't answer the why questions. Why are there laws at all? Why does mathematics describe reality? Why does anything exist? These are questions that science touches but cannot fully resolve. And you know what? I think that's okay. I think it's more than okay. I think it's wonderful, because it means there's room for wonder, room for mystery, room for different ways of knowing, and different frameworks for understanding. The fact that physics can describe a self-creating universe doesn't diminish the awe I feel when I contemplate existence. If anything, it deepens it. Because here's what quantum cosmology is really telling us. The universe is far stranger than we ever imagined. It's not just strange in its details, quantum entanglement, black holes, dark energy. It's strange in its very existence. The boundary between being and non-being, between something and nothing, between existence and the void, these boundaries are not sharp, they're quantum. They're fuzzy. They're subject to probabilities and superpositions and all the weirdness that makes quantum mechanics so fascinating and so frustrating. So as we move forward, as we dive deeper into these ideas, I want you to hold on to that sense of strangeness. Don't let the equations and the technical jargon fool you into thinking we've got it all figured out. We don't. We're explorers, mapping out new territory, and the map is full of blank spaces marked, "Here be dragons." But those dragons, they're not threats, they're invitations. They're calling us to look closer, to think harder, to imagine more boldly. And in the next part of our journey, we're going to answer that call. We're going to explore what nothing really means in physics. We're going to look at how quantum mechanics and general relativity combine to create the possibility of spontaneous universe creation. We're going to meet some of the key players in this scientific drama, from Alan Guth's inflationary universe, to Stephen Hawking's imaginary time, to Lawrence Krauss's universe from nothing. And we're going to confront head-on the philosophical objections, the theological concerns, and the conceptual puzzles that these ideas raise. Because this isn't just about physics. This is about what it means to exist, what it means to understand, and what it means to ask the biggest questions we can ask. The universe had a beginning, or did it? It emerged from nothing, or did it emerge from something we don't yet fully understand? The laws of physics explain everything, or do they just push the mystery back one level? These are the questions that keep me up at night. These are the questions that make physics not just a profession, but a calling. Now, before we move to the next part, I want to spend a little more time on something that's absolutely foundational to everything we're discussing, the quantum vacuum. Because when physicists say the universe could emerge from nothing, what we really mean is that it could emerge from the quantum vacuum. And understanding what that is, really understanding it, is crucial. So let's talk about what empty space actually is. In your everyday experience, empty means, well, empty. No stuff. If I take a box and pump out all the air, all the molecules, every last atom, I've got empty space, right? That's what Newton would have said. That's what common sense says. But quantum mechanics tells us something profoundly different. It tells us that you can never truly empty that box. You can remove all the particles, sure, but you can't remove the fields. What's a field? Well, think about the electromagnetic field. It's what allows charged particles to interact with each other. It's what carries light from the sun to your eyes. Even when there are no particles present, the field is still there, pervading all of space. And according to quantum mechanics, this field is never completely still. It's always fluctuating, always jittering. Even in its lowest energy state, the ground state, the vacuum state, These fluctuations are not optional. They're required by the Heisenberg uncertainty principle. You cannot have a quantum field that sits perfectly still at zero energy, because that would mean you know both its value and its rate of change with perfect precision, which quantum mechanics forbids. The field must fluctuate. And these fluctuations can briefly manifest as pairs of particles, what we call virtual particles. Let me give you a concrete example. In the vacuum around us, right now, electron-positron pairs are constantly popping into existence. An electron, negatively charged, and a positron, its antimatter partner, positively charged, appear, exist for a tiny fraction of a second, and then annihilate back into the vacuum. They never live long enough to be directly detected, but their effects are real and measurable. They alter the energy levels of electrons and atoms by a tiny amount, an effect called the Lamb shift, which has been measured to extraordinary precision and matches the predictions of quantum field theory perfectly. So when we talk about the universe emerging from nothing, we're talking about it emerging from this quantum vacuum, a state where there are no particles, but where quantum fields exist and fluctuate. Now, you might say, but Brian, that's not nothing. That's something. And you're right. That's exactly the point that philosophers like David Albert make. The quantum vacuum has structure, has laws, has properties. It's not the philosopher's nothing, the absolute absence of anything. It's the physicist's nothing, the lowest energy state of fields that pervades space-time. But here's the remarkable thing. Even this physicist's nothing might not be the deepest level, because the quantum fields themselves exist in space-time, and space-time is also a dynamical entity according to general relativity. So we can ask, could space-time itself emerge from an even deeper nothing? Could the quantum fields themselves emerge? And this is where we need quantum gravity, a theory that treats not just matter and energy quantum mechanically, but space and time themselves. And here's where it gets truly wild. In quantum gravity, space-time isn't this fixed stage on which events play out. It's part of the quantum show. It can be in superpositions, it can fluctuate, and at the Planck scale, about 10 to the power of minus 35 meters, far smaller than an atom, space-time itself becomes grainy, foamy, uncertain. The very notion of a smooth geometric space breaks down. Some physicists, like Lawrence Krauss, argue that this is as close to true nothing as we can get a state where even space-time hasn't yet taken form, where only the abstract laws of quantum gravity exist. And from this state, universes can spontaneously nucleate like bubbles forming in boiling water. The laws allow it, the mathematics describes it, and nothing prevents it. But now we're back to that deeper question. Where do the laws come from? If universes can emerge from nothing, but that nothing obeys quantum mechanical laws, then those laws themselves are something. They're not physical entities, not particles or fields or space-time geometries. They're abstract mathematical structures. But they're something nonetheless. So, have we really explained creation from nothing? Or have we just pushed the question back to why these laws and not others? This is not a question physics can answer, at least not physics as currently practiced. We can discover what the laws are, we can test them, refine them, unify them. But asking why those particular laws exist rather than others, that's what philosophers call a metaphysical question. It's beyond the reach of experimental verification. Now, some physicists are comfortable with that. They say, look, the laws just are. They're brute facts about reality, and there's nothing deeper to explain. Others think there might be a deeper level, a theory of everything, that not only unifies all the forces, but explains why the universe must have the particular laws it does. Maybe there's only one mathematically consistent way for a universe to exist, and we're gradually discovering what that is. Maybe, as Stephen Hawking once suggested, the universe exists simply because it would be mathematically inconsistent for it not to exist. But let me be honest with you. These are speculations. Beautiful, intriguing speculations, but speculations nonetheless. We don't have a theory of everything. We don't have a complete theory of quantum gravity. And we certainly don't have a mathematical proof that the laws of physics are the only logically possible laws. What we do have is something remarkable enough. We have frameworks that show how the universe could begin without violating physical law. We have theories that are mathematically consistent and that make predictions we can test. And we have a growing recognition that the origin of the universe is not forever beyond the reach of science. Let me tell you about one more idea that's going to be important as we move forward: cosmic inflation. In the early 1980s, a physicist named Alan Guth proposed a remarkable solution to some puzzles about the Big Bang. He suggested that in the first tiny fraction of a second after the universe began, it underwent a period of exponentially rapid expansion, expanding by a factor of at least 10 to the power of 26 inches, less than 10 to the power of minus 32 seconds. This sounds crazy, I know. But inflation solves several problems. It explains why the universe is so uniform on large scales, because regions that are now separated by billions of light years were once close enough to reach thermal equilibrium before inflation blew them apart. It explains why the universe is so flat, because inflation stretches out any initial curvature, like blowing up a balloon until its surface looks flat. And it explains the origin of the tiny fluctuations we see in the cosmic microwave background, because quantum fluctuations during inflation get stretched to cosmic scales and frozen in as density variations that eventually become galaxies. But here's what's really interesting for our discussion. During inflation, the energy driving the expansion comes from what's called an inflaton field, a hypothetical quantum field that exists in a high-energy state. As the universe expands, this field slowly rolls down to a lower energy state, and when it reaches the bottom, the energy gets converted into particles and radiation, the hot Big Bang. So inflation provides a mechanism for converting the vacuum energy of a quantum field into the matter and energy we see around us. And here's the kicker: in some versions of inflation, particularly eternal inflation, the process never fully stops. In most regions, the inflaton field reaches its minimum and inflation ends, creating a pocket universe like ours. But in other regions, quantum fluctuations can boost the field back up, causing inflation to continue. This creates a vast multiverse, an infinite collection of pocket universes, each potentially with different properties, different laws, different values for the fundamental constants. Now, why am I telling you this? Because the multiverse has profound implications for the question of cosmic origins. If there's a multiverse, and if different pocket universes can have different properties, then the fact that our universe seems fine-tuned for life is no longer surprising. We exist in one of the universes where the conditions happen to be right. The vast majority of universes might be sterile, lifeless, but we wouldn't be around to observe those. We're necessarily in a universe capable of supporting observers, a principle called the anthropic principle. This is hugely controversial. Some physicists love the multiverse because it solves the fine-tuning problem elegantly. Others hate it because it seems to give up on the goal of explaining why our universe has the particular properties it does. If anything goes somewhere in the multiverse, then our theories lose predictive power. We can't say the electron must have this mass because of this deep principle. We can only say in our universe the electron happens to have this mass. But here's what I find fascinating. Whether you like the multiverse or not, it emerges naturally from our best theories of inflation and quantum mechanics. We didn't invent it to solve philosophical problems. We discovered it, or at least found it to be a generic consequence of ideas we developed for completely different reasons. And that's often how physics works. You're studying one thing, and something else, something unexpected and profound, falls out of the equations. So let me pull together where we've been. We've seen that the universe appears to have had a beginning about 13.8 1.8 billion years ago. We've seen that quantum mechanics allows particles and potentially entire universes to appear spontaneously from vacuum fluctuations. We've seen that the total energy of the universe might be zero, making such a spontaneous appearance energetically free. We've seen proposals like the Hartle-Hawking no-boundary condition that describe the universe's quantum state without invoking an external cause. And we've seen how inflation could generate a vast multiverse of pocket universes with varying properties. All of this adds up to a remarkable conclusion. The laws of physics, as we currently understand them, are capable of accounting for the origin and evolution of the universe without requiring anything beyond those laws. No supernatural intervention, no first cause, no unmoved mover, just quantum mechanics, general relativity, and the fields and particles they describe. But, and this is crucial, this doesn't mean we've explained everything. We haven't explained why there are laws at all. We haven't explained why mathematics works so unreasonably well in describing the physical world. We haven't explained consciousness or meaning, or why the universe contains these particular structures rather than others. And we certainly haven't explained why there's something rather than nothing at the deepest possible level. What we've done is show that you can have a universe without a divine creator if you grant the existence of physical laws and quantum fields. But those laws and fields are themselves something. They have structure, they have properties, they have causal power. So in a sense, we've translated the question, why is there something rather than nothing, into why are there laws of physics? And that's progress. It's real progress, but it's not a final answer. You know, Einstein famously said, the most incomprehensible thing about the universe is that it is comprehensible. What he meant was that it's astonishing that we evolved primates on a small planet can understand the deep structure of reality using mathematics and experiments. There's no obvious reason why the universe should be intelligible to us, and yet it is. This intelligibility is itself a kind of mystery. The laws of physics are elegant, mathematical, universal. They hold at the edge of the observable universe just as they hold in this room. They held a microsecond after the Big Bang, and they'll hold trillions of years in the future. Why? Why should the universe be governed by laws at all, let alone laws with such beauty and economy? Some people see in this an argument for design. The laws are fine-tuned, elegant, and life-permitting. Surely that points to a cosmic designer. Others see in it simply a brute fact, or perhaps a consequence of deeper mathematical necessity. And still others see in it an invitation to further scientific inquiry. Maybe we'll discover a deeper level of explanation that tells us why the laws must be as they are. I don't know the answer. I don't think anyone does. But what I do know is that the question itself is profound, and that grappling with it using the tools of physics, philosophy, and theology is one of the great intellectual adventures of our time. Let me share with you one more thought experiment before we wrap up this first part. Imagine that you're trying to explain to someone from the 18th century, say Thomas Jefferson or Immanuel Kant, what modern physics has discovered about cosmic origins. How would you even begin? You'd have to explain relativity, that space and time are interwoven, that gravity is curvature, that the speed of light is absolute. You'd have to explain quantum mechanics, that particles are waves, that outcomes are probabilistic, that measurement affects reality. You'd have to explain the expansion of the universe, the Big Bang, the cosmic microwave background, and then you'd have to explain that we can write down equations describing the quantum state of the entire universe, including its origin. Your 18th century interlocutor would think you were insane, or a mystic, or both. Because what you're describing is so far removed from everyday experience, so contrary to intuition, that it sounds like mythology or metaphysics rather than science. And yet, it's science. It's based on observations, experiments, mathematical rigor. We've seen the evidence for expansion in the redshift of distant galaxies. We've detected the cosmic microwave background, the afterglow of the Big Bang with exquisite precision. We've measured the effects of virtual particles on atomic spectra. We've confirmed the predictions of quantum field theory and general relativity in countless experiments. This isn't speculation. It's our best understanding of how the universe actually works. But here's what I find so beautiful about this. The fact that the universe is so strange, so far beyond our intuitions, so much more subtle than anything we could have guessed, that's not a bug, it's a feature. It means reality is richer than we imagined. It means there's always more to discover. It means that the process of science is not just about confirming what we already suspect, but about being surprised, being humbled, being forced to expand our conceptual horizons. When Niels Bohr, one of the founders of quantum mechanics, was confronted with someone who found quantum theory hard to accept, he supposedly said, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet." The same is true for cosmology. If the idea that the universe could emerge from a quantum fluctuation doesn't shock you, doesn't seem bizarre and counterintuitive and almost magical, then I haven't done my job in conveying just how strange this all is. But strange doesn't mean wrong. In fact, in physics, strangeness is often a sign that you're onto something deep. Nature doesn't care about our intuitions. Nature doesn't care whether we find its behavior sensible or shocking. Nature just is, and our job is to figure out what it is, not to insist that it conform to our preconceptions. So as we move forward, as we dive deeper into quantum cosmology and the details of how universes might begin, I want you to embrace the strangeness. Don't try to force these ideas into familiar boxes. Let them expand your sense of what's possible, because the universe is under no obligation to make sense to you. But it is giving you the tools, mathematics, observation, experiment, to understand it on its own terms. And those terms, they're astonishing. They involve imaginary time and quantum superpositions and vacuum energy and space-time foam. They involve universes that create themselves, laws that emerge from deeper laws, being that arises from the boundary of non-being. It's strange, it's beautiful, and it's the best answer we have, given everything we've learned over the past century of revolutionary physics. In the next part, we're going to get into the details. We're going to explore the mathematics of quantum cosmology, the debates over different proposals for the wave function of the universe, the experimental evidence that constrains these ideas. We're going to look at the objections, both scientific and philosophical, and see how physicists are responding to them. And we're going to confront directly the question of what it all means for the existence of God. Because here's the thing, this isn't just an academic debate. For many people, the origin of the universe is intimately tied to their deepest beliefs about meaning, purpose, and the divine. And what physics is telling us, what it's been telling us with increasing clarity over the past few decades, is that those beliefs cannot rest on the assumption that the universe must have had a supernatural beginning. The natural laws might be sufficient. Does that invalidate belief in God? No. Many of the physicists who develop these ideas are themselves religious. They see the laws of nature as God's way of creating, or they see the existence of laws as itself requiring divine explanation. But it does mean that if you believe in God, you can't point to the beginning of the universe and say, see, science can't explain that, so God must have done it, because science is explaining it. Maybe not completely, maybe not finally, but substantially enough that the God of the gaps argument doesn't work anymore. What remains then is a different kind of theological question. Not did God create the universe, but what is the relationship between God and the laws of nature? Are those laws themselves divine? Are they God's thoughts? as some philosophers and theologians have suggested, or are they separate from God, constraints even on divine action? These are profound questions, and they're questions that physics touches but cannot resolve, and that's okay. That's how it should be. Science and religion are different ways of engaging with reality, different frameworks for asking and answering questions. Where they overlap, there should be dialogue, debate, and mutual respect. But they're not the same, and they're not in competition for the same territory, at least not in any simple way. What I'm offering you in these three parts is the scientific side of that dialogue. I'm showing you what physics has discovered, what it suggests, and what it leaves open. I'm not telling you what to believe about God. That's your choice, informed by your experiences, your traditions, your philosophical commitments. What I'm telling you is that the choice can no longer rest on the assumption that physics has nothing to say about cosmic origins. Physics has a lot to say. And what it's saying is extraordinary. So get ready. Because in part 2, we're going to dive deep. We're going to explore the quantum nature of space-time, the different proposals for how universes begin, and the fascinating ways that modern physics is testing these ideas. We're going to meet the key players in this drama, not just Hawking and Hartle, but Vilenkin and Linda and Guth and Penrose and many others who've contributed to our understanding. And we're going to grapple with the hardest questions. What does nothing really mean? Can the laws of physics explain themselves? And what, if anything, lies beyond the reach of scientific explanation? These are big questions, the biggest questions, and I can't promise you we'll find final answers. But I can promise you that the journey, the process of thinking deeply about these mysteries using the tools of modern physics is going to be one of the most rewarding intellectual adventures you can have. Because at the end of the day, what we're really asking is, what is the nature of existence itself? And that's not just a physics question. It's a human question. It's the question that has driven philosophers and theologians and mystics and scientists for thousands of years, and now, for the first time, we have the tools to approach it scientifically. We may not reach the final answer, but we're getting closer. And the view from here is spectacular. So we'd arrived at this surprising point where modern physics, quantum mechanics, and general relativity has given us frameworks that describe how universes might come into being without requiring an external cause, without invoking a creator. We explored the Hartle-Hawking no-boundary proposal. We saw how the quantum vacuum seethes with activity. And we understood that the universe's total energy might be zero. But here's the thing, and this is where we really need to roll up our sleeves. Those are not the only proposals on the table. And the debates between these different approaches, they reveal something profound about the limits and possibilities of scientific explanation. Let me introduce you to another key player in this story, Alexander Vilenkin. Now, Vilenkin, who's at Tufts University, has spent decades developing a competing idea for the wave function of the universe, and his approach is fundamentally different from Hartle and Hawking's. It's called the tunneling wave function, and you know what? It might actually be a better description of how our universe began. Here's the core difference. Remember how Hartle and Hawking used imaginary time to make the beginning of the universe smooth and boundary-free, like the surface of a sphere? Well, Vilenkin said, wait a minute. That's mathematically elegant, sure, but does it actually describe what happened? Instead, he proposed that the universe literally tunneled into existence from nothing, and by nothing, he means a state with zero size, no space, no time, no classical geometry whatsoever. Now, this is bizarre, I know, but let me explain what quantum tunneling is, because once you get it, Vilenkin's idea becomes, well, not less bizarre, but at least comprehensible. In ordinary quantum mechanics, particles can do something that would be absolutely forbidden classically. They can pass through barriers that they don't have enough energy to climb over. It's like rolling a ball toward a hill and watching it mysteriously appear on the other side, even though it never had the energy to get to the top. The ball doesn't go over the hill, it goes through it. This isn't science fiction. This happens. Radioactive decay, for example, is a tunneling process. The nucleus of a uranium atom has particles trapped inside by a potential energy barrier. Classically, they shouldn't be able to escape. But quantum mechanically, there's a probability, a small but non-zero probability, that they tunnel through that barrier and escape. And when enough time passes, that's exactly what happens. The nucleus decays. Vilenkin's audacious proposal is that the entire universe underwent a similar process. There's a quantum state representing nothing, zero size, zero volume, no space-time, and then there's another state representing a small finite universe with a tiny bit of space and time. Between these states, there's a barrier, an energy barrier, that would classically prevent the transition, but quantum mechanically, the universe can tunnel through that barrier, appearing spontaneously on the other side as a tiny, finite de Sitter space, a small universe filled with vacuum energy that then inflates, expands, and evolves into the cosmos we see today. Now, you might be asking, okay, but what determines whether you get Hartle-Hawking's smooth beginning or Vilenkin's tunneling beginning? And that's a fantastic question. It turns out that the two proposals make different predictions, and in principle, we might be able to test them. The key difference shows up in something called the amplitude of fluctuations in the early universe. You see, both proposals predict quantum fluctuations, tiny variations in the density of the universe that eventually grow to become galaxies and clusters of galaxies. We can see the imprint of these fluctuations in the cosmic microwave background radiation, that faint afterglow of the Big Bang that pervades all of space, and different wave functions for the universe predict slightly different patterns of fluctuations. Hartle and Hawking's proposal tends to predict a universe that starts off very smooth with small fluctuations. Vilenkin's tunneling wave function, on the other hand, can produce larger fluctuations depending on the details of the tunneling process. So when we measure the cosmic microwave background with exquisite precision, which we've been doing with satellites like Planck, we're actually testing these competing ideas about how the universe began. Now, here's where it gets interesting, and this is something I really want you to appreciate. Stephen Hawking and Alex Vilenkin were friends, colleagues, but they disagreed about this. And you know what Vilenkin once said? He said that Stephen and he disagreed about minor things, quote, like the sign and the wave function of the universe. The sign, whether it's plus or minus in a particular equation. That might sound trivial, but that sign determines whether you get a no-boundary proposal or a tunneling proposal. It determines whether the universe emerges smoothly from imaginary time or tunnels abruptly from zero size. And both of these brilliant physicists spent years developing and defending their respective approaches. What does that tell you? It tells you that we're operating at the absolute frontier of human knowledge. We have mathematical frameworks that are consistent, that don't violate known laws of physics, but we don't yet know which one, if either, correctly describes reality. And that's okay. That's how science works. You develop competing hypotheses, you make predictions, you test them. The fact that we can even formulate these questions mathematically is astonishing. But let me take you deeper, because there's a third approach I need to tell you about, and it's radically different from both Hartle-Hawking and Vilenkin. It's called loop quantum gravity, or LQG for short, and it's been developed over the past few decades by physicists like Abhay Ashtekar, Carlo Rovelli, Lee Smolin, and many others. And in loop quantum gravity, space-time itself is fundamentally discrete. Now, what do I mean by that? Well, in ordinary quantum mechanics, we learned that energy comes in discrete packets called quanta. In loop quantum gravity, the same is true for space and time. There's a smallest possible unit of volume, about 10 to the power of minus 105 cubic meters, the Planck volume. There's a smallest possible unit of area, about 10 to the power of minus 70 square meters, the Planck area. And below those scales, the very concepts of space and time break down. Imagine zooming in on the fabric of space-time with a microscope that can see smaller and smaller scales. At everyday scales, space-time looks smooth, like the surface of a calm ocean. But as you zoom in closer and closer, you start to see quantum fluctuations, like ripples on the water. And when you get down to the Planck scale, 10 to the power of minus 35 meters, you find that space-time isn't smooth at all. It's made of discrete chunks, like pixels on a screen. These chunks are woven together into what's called a spin network, a graph whose nodes and edges carry quantum numbers that describe the geometry of space. Now, why does this matter for the origin of the universe? Because in loop quantum cosmology, the application of loop quantum gravity to the early universe, something remarkable happens when you run the clock backward toward the Big Bang. In classical general relativity, you hit a singularity, a point where the equations break down and physical quantities become infinite. But in loop quantum cosmology, you don't hit a singularity. Instead, you hit a bounce. Let me say that again, because it's important. Loop quantum cosmology predicts that the Big Bang singularity is replaced by a big bounce. The universe doesn't begin at a singular point. Instead, it was contracting before it was expanding. As the universe contracts, gravity becomes stronger and stronger, and in classical general relativity, this leads inevitably to a singularity. But quantum gravity effects kick in at extremely high densities around the Planck density, which is about 10 to the power of 97 kilograms per cubic meter. At that point, gravity becomes repulsive rather than attractive, and the contraction halts and reverses. The universe bounces, and the expanding phase begins. Now, this is a completely different picture from what we've been discussing. It's not a universe emerging from nothing. It's a universe that had a previous phase, a contracting phase before the bounce. And you might be thinking, okay, but doesn't that just push the question back? Where did the contracting phase come from? And you're right, it does. But here's the key insight. In loop quantum cosmology, the notion of a beginning might not even make sense. The universe might be eternal, bouncing from contraction to expansion to contraction in an infinite cycle. Or, and this is where it gets really wild, the bounce might be something that happens not just once, but constantly in different regions of space-time. Maybe our observable universe is just one bounce in a vast sea of bounces, each creating a pocket universe with its own properties, its own history. Now, I want to pause here and emphasize something. Loop quantum gravity, like string theory, is not yet a complete theory. We don't have all the equations worked out. We can't yet make detailed predictions about every observable quantity, but what we do have is a consistent mathematical framework that resolves singularities, that makes space-time discrete at the Planck scale, and that connects in a natural way to general relativity at larger scales. And that's progress. Real, substantial progress. So now we have three different approaches on the table. Hartle-Hawking's no-boundary proposal, Vilenkin's tunneling wave function, and loop quantum cosmology's big bounce. And you know what's fascinating? They're not necessarily mutually exclusive. It's possible, and this is current research, that they're different descriptions of the same underlying reality viewed from different mathematical perspectives. Think about it this way. Imagine you're describing a mountain. You could describe it from the north side, from the south side, from above. Each description would look different, would emphasize different features, but they're all describing the same mountain. Similarly, these different approaches to quantum cosmology might be different ways of describing the same quantum reality. But here's what I really want you to understand. All three of these approaches, and there are others I haven't even mentioned, share a common feature. They treat the origin of the universe as a problem that physics can address. They don't say, well, the beginning is beyond the reach of science, so we need to invoke God or some other non-physical explanation. They say, let's apply the laws of quantum mechanics and general relativity to the universe itself and see what we get. And what we get is astonishing. We get proposals where universes can emerge from quantum fluctuations, where the Big Bang singularity is replaced by a bounce, where space-time itself is quantized and discrete. We get predictions that we can test with observations of the cosmic microwave background, with measurements of gravitational waves, with studies of the large-scale structure of the universe. Now, let me address something that's probably been nagging at you this whole time. When physicists talk about the universe emerging from nothing, what do we really mean by nothing? Because the quantum vacuum isn't nothing. It has fields, it has fluctuations, it has energy. The tunneling state isn't nothing. It's a quantum state with specific mathematical properties. Even in loop quantum gravity, the state before the bounce isn't nothing. It's a contracting universe with matter and energy. So, have we really explained creation from nothing? Or have we just defined nothing in a way that's actually something? This is where the philosopher David Albert, among others, has raised serious objections. Albert points out that the physicist's nothing is not the same as the philosopher's nothing. When philosophers talk about nothing, they mean the absolute absence of anything. No space, no time, no matter, no energy, no laws, no quantum fields, nothing. Literally nothing. And Albert's right. The quantum vacuum is not that. It's a state with very specific properties, governed by very specific laws. So when Lawrence Krauss wrote a book titled A Universe from Nothing and claimed that physics had explained how you could get something from nothing, Albert pushed back hard. He said, look, you haven't explained how you get something from nothing. You've explained how you can get one kind of something, a universe from another kind of something, a quantum vacuum or a quantum state. That's interesting, that's important, but it's not the same as explaining true creation from absolute nothingness. And you know what? I think Albert has a point, but I also think that point is actually profound in a way that goes beyond scoring philosophical points. Because what it reveals is that physics, as currently practiced, always starts with something. It starts with laws, with mathematical structures, with quantum fields. And those starting points are themselves something. They have properties, they have structure, they have explanatory power. So the question, why is there something rather than nothing, gets transformed into, why are there laws? Why does mathematics describe reality? Why does quantum mechanics work? And these questions, these deeper questions, might not be answerable by physics, at least not by physics as we currently understand it, because physics is the study of how systems evolve according to laws. But asking where the laws themselves come from, that might be a question that requires a different kind of inquiry. Now, some physicists try to push further. Max Tegmark, for example, has proposed something called the mathematical universe hypothesis. The idea is that physical reality isn't just described by mathematics, it is mathematics. The universe is literally a mathematical structure, and the reason mathematics works so well in describing physics is that there's no distinction between the mathematical description and the physical reality. If Tegmark is right, then asking why there are laws of physics is like asking why 2 + 2 = 4. It's not that something made it that way, it's that it couldn't be any other way. Mathematical truths are necessary truths, and if physical reality is mathematical, then physical truths are also necessary. The universe exists because it would be mathematically contradictory for it not to exist. Now, I find this idea both beautiful and unsatisfying. Beautiful because it's so elegant, so economical, it doesn't require anything beyond mathematics itself. But unsatisfying because it doesn't really explain why this particular mathematical structure, the one corresponding to our universe, exists, rather than some other mathematical structure, or all mathematical structures, or none at all. It pushes the question back, but it doesn't fully answer it. And here's where I think we need to be honest about the limits of what physics can tell us. Physics is extraordinarily successful at explaining how things work. Give me a system, tell me the initial conditions and the laws that govern it, and I can predict what happens next with astonishing accuracy. We can predict the motion of planets, the behavior of atoms, the evolution of stars, the expansion of the universe. Physics is the most successful intellectual enterprise in human history. But there are questions that physics, by its very nature, might not be able to answer. Questions like, why do these particular laws exist? Why does anything exist at all? What is the ultimate ground of being? These are questions that have traditionally been the domain of philosophy and theology, and it's not clear that they can be fully resolved by scientific methods alone. Now, that doesn't mean we should stop trying. One of the things I love about physics is that we keep pushing the boundaries, keep asking questions that seem unanswerable, and sometimes, often, we find ways to make progress. 100 years ago, people would have said that the beginning of the universe was forever beyond the reach of science. And yet here we are, with mathematical frameworks that describe it, with observations that test those frameworks, with real substantive progress toward understanding cosmic origins. So maybe, just maybe, the questions about why there are laws and why anything exists are not forever beyond reach. Maybe we'll develop new mathematical tools, new conceptual frameworks, new ways of thinking that allow us to go deeper. Or maybe, and this is equally fascinating, we'll discover that there is a fundamental limit to what can be explained, a point beyond which science cannot go, not because we're not smart enough or don't have the right instruments, but because the very nature of explanation itself runs into a wall. Let me give you an analogy. Imagine you're trying to explain why something is true by deriving it from something more fundamental. You explain phenomenon A by showing it follows from law B. You explain law B by showing it follows from deeper principle C. You explain principle C by showing it follows from even more fundamental structure D. But this chain of explanation has to stop somewhere. Eventually, you reach something that cannot be explained in terms of anything more fundamental, because there is nothing more fundamental. That ultimate foundation, whatever it is, has to be what philosophers call a brute fact, something that just is, without further explanation. Now, where does that brute fact lie? Is it the laws of quantum mechanics? Is it the mathematical structure of reality? Is it some deeper principle we haven't yet discovered? Or is it God, a conscious being, who chose to create a universe with these particular laws? Physics can push that boundary back. We can show that what seem like brute facts are actually consequences of deeper principles, but we can't eliminate the need for some ultimate foundation entirely. There has to be something that grounds everything else, something that doesn't itself require further explanation. And here's what I find beautiful about this. Whether you're a physicist or a philosopher or a theologian, you're grappling with the same fundamental mystery. We're all trying to understand why there's something rather than nothing, why the universe has the structure it does, why we're here to ask these questions in the first place. For the physicist, the tools are mathematics and observation. For the philosopher, the tools are logic and conceptual analysis. For the theologian, the tools are scripture and spiritual insight. These approaches can inform each other, can learn from each other, can challenge each other, but they're not the same, and that's okay. What physics offers is not a complete answer to the question of cosmic origins, but a framework for understanding how a universe with certain properties can come into being, governed by certain laws, without requiring external intervention at the moment of creation. And that framework is based on our best current understanding of quantum mechanics and general relativity, two theories that have been tested more rigorously than any theories in the history of science. But, and this is crucial, that framework takes the laws themselves as given. It doesn't explain why there are laws. It doesn't explain why quantum mechanics, rather than some other set of rules, it doesn't explain why mathematics works. It starts with those ingredients and shows what follows. Now, is that a limitation? Yes, in a sense. But it's also what makes physics powerful. By focusing on how things work rather than why things are, physics can make precise, testable predictions. We can build experiments, we can make observations, we can check our theories against reality, and when our theories fail, when predictions don't match observations, we learn something profound. We're forced to revise our understanding, to develop better theories, to go deeper. And that process, that iterative process of hypothesis, prediction, testing,